For this illustration, please open the dataset on Blackboard titled Original Salary Data Increased by 10 Times. And so what I did for this dataset is I took our original data, the salary and the pubs, etc., and there was the N of 62, and what I did is I just increased it 10 times. So I made 10 separate cases for case 1, all exactly alike. In case 2, I made 10 cases for that. In case 3, 10 cases. So we ended up with, in the new file, 620 total cases. And the thing I wanted to illustrate to you is the difference between effect size and significance. So effect size is not dependent on n size, but significance is. So the significance just indicates the confidence by which we know that what's going on in our sample is reflective of what's going on in the population. And so what I did is I just did the same analysis that we just did in the previous lesson and the screencast, where we regressed salary on pubs and time since PhD, and I did it in both files, on both the 62 size and the 620 size. And so what I'm expecting is that the R-square will not change, but the confidence by which we can be sure of that R squared will increase with an increased sample size. Okay, so both we know are significant, right, because we ran the analysis and it is significant in the 62 n size sample. But I'm predicting that the error will decrease for the one with more people. The error and the residual will decrease, and so we can have more confidence in those results. And again, significance just means that we have more confidence that what we see in our sample is indicative of what's going on in the population. Okay, so I just put these outputs here together. This is what you should get when you run it as well, but I just put them side by side so we can compare. All right, so we have exactly the same R and R squared, just like I thought. The adjusted R square is different, but it's not different by much, and we'll go over that later, so it's not a big deal. Our SEE has changed from 7,700 in the first sample to 7,500 in the second sample. So remember, the SEE is the standard deviation of the distribution of residuals, and it is an index of the error in our data. So we can see that the bigger sample size has decreased it a little bit. But that's not the most interesting part to me. The most interesting part is looking at the sum of squares residual in both cases and seeing that it's the exact same. Do you see that it is, it looks like it's 3.501, and then in the one sample, the 62 sample, and then it's the same, 3.501 in the larger sample. So whoop-de-ding, it doesn't seem to be making a difference. However, the mean square error is going to be a big deal. So what we see with that is that we're dividing the sum of squares residual by 59 in the first case, but we're dividing it by 617 in the second case. So what we have done is we've really reduced our mean square. We are able to cut into that big time, and in the second sample that we weren't able to do in the first sample. So that's why n matters, is because we are cutting into the denominator of the mean square error and making it much smaller, thereby making the whole term much bigger, because we're going to divide that small term into the mean square for regression. And of course we want the mean square regression to be very large. So the smaller the denominator, the better, because once we divide that in, it's going to get very large. So that is the reason, ladies and gentlemen, is the reason why increasing n size does not affect effect size at all, but it does impact the confidence with which we can say that this is what is going on in the population of interest. So, one more thing. Look at the F size between the 62 versus the larger sample. It's an F size of 18.9 in the smaller sample, and it goes up to 197 in the second. So that is huge. So you can see, it's so cool because you can see exactly why N size matters. You don't just, it's not just like, oh, the bigger the N, the better, because I'm not sure why, but it just is. No, I mean, you can actually see the math working in this case. And that's what's so awesome about learning, I think, is just being able to see it come to light and having those moments of aha. So let's say you get asked a question about maybe somebody thinks that you would have gotten a bigger effect if you had increased your N. Let's say you're at a conference and somebody's like, oh, you should have increased your N because you would see a bigger effect. And you could tell them, no, I wouldn't see a bigger effect, but I might have significance, whereas right now I didn't quite find significance. But if I had a larger N, then the effect size would still be the same, but I would be able to see significance. And so, with a smaller N, it's more likely that you can have a nice effect size, but not quite get over the top of significance. And that's because we need a big DF to cut into that residual sum of squares in order to have a small mean square residual that will in turn make a large F statistic that will hopefully be significant. So it all comes back to ANOVA, really. The ANOVA table kind of never leaves us. It's just interpreted slightly differently here in regression, but the basic concepts are all really the same and consistent throughout.